All right, calculus, the second graph we're going to do for our final algorithm. So I assume you have that in front of you. You can refer to it. The first step that we're going to take is to look for discontinuities. There aren't any. We have a polynomial function, but you've indicated by writing this that you thought about it. Step 2 is to look for asymptotes. I think I said that wrong. Asymptotes. There is no vertical asymptote. As we look at the end behavior, as x gets really, really large, to the left and to the right, there are no horizontal or oblique asymptotes either. This is a polynomial function. Let's just write none, it's shorter. There we go. Number 3. So this is looking pretty easy. We look for intercepts. They're just really nice nice points. Zeros are lovely. So for my y-intercept, it's 0, 0. For my x-intercepts, I want to know when that function is 0. Now, not everything I give you is going to be beautiful, but this one, at the very least, you can factor out an x. And all of you know the factor theorem like so well, and you're like, I know that if I substituted a 1 into that, I would get a 0. So it must have a factor of x minus 1. If you divide x minus 1 into that thing, you will get, I'm going to do this in my head just a second. Oh, and you say, golly, that's lovely. This factors nicely to a positive 2 and a negative 1. So we can write that as x minus 1 squared, x plus 2, and that would only take you 5 seconds, right, to do the factor theorem in your head. And you would come up with the fact that you have some beautiful roots, a double at 1, 1 at 0, and negative 2. So those are going to be lovely points for us to use. All right, number 4 and 5. We'll just do those together. We're going to look for critical points, and we're going to determine if they're max or min. Okay, so for critical points, I need to know where my derivative is 0 or undefined. This one will not be undefined. Our derivative is 4x cubed. Subtract 6x plus 2. I'm going fast, but I know you guys are speedy. I want to know where that thing is 0. Again, with the factor theorem, if you had noticed at x equals 1, we have a 0. So I know at the very least that this has an x minus 1 factor. So when I do long division into that, I get 4x squared plus 4x subtract 2. So far, this one was super easy for intercepts. Well, decently easy for intercepts, super easy for asymptotes. But it's getting a little tricky here as we go through the critical points. Right. So, ugly. I can tell that's not nicely factorable, so I'm going to use the quadratic formula. I know that x equals 1 is one of my critical points. If I use the quadratic formula, I get x equals negative 1.4 and x equals positive 0.4. So the quadratic formula. Okay. We have 3 critical points, so our chart is going to get a little bit ugly. But I want to look at, okay, let's get these in the right order. I've got negative 1.4, I've got 0.4, and I've got 1. So I want to look to the left. Here, I'm going to move him over. I want to look to the left of negative 1.4. I want to look in between. I want to look in between 0.4 and 1 and to the right of 1. Wow. Okay, so I look at my first derivative and all I need is a sign, positive or negative. So there's my zeros. For my first derivative, I need to have a look at that. Okay. If x is less than negative 1.4, a negative 2, for example, so I'm looking here, 4x cubed would be negative, negative 6x would be positive, and so I'm using negative 2, so I have negative 16 plus 12, and negative 4 plus 2 is negative. You can use a calculator for this. Between negative 1.4 and 0.4, I would use 0, so we're going to have positive. Between 0.4 and 1, maybe 0.5. Okay, I am getting negative. And then greater than 1, say that we did 2, so it would be 4 times 8. 32 take away 12 is positive, plus 2 is positive. Okay, you can use a calculator for that. We're just looking at the first derivative, and that tells us about our function, that it is decreasing and then increasing, so we have a minimum. And then it decreases again, so we must have a maximum. And then it increases over here, so we must have a minimum again. All right. Number 6 is where we do the second derivative test. So we look for concavity. I want to know where the second derivative is 0 or undefined. This one will not be undefined. But first derivative is 4x cubed minus 6x plus 2, so 12x squared minus 6. Okay. When is that equal to 0? Whenever x squared is 0.5. I am imposing a square root, so I have to consider the positive and negative square root of 0.5, which is about 0.7. All right, for my second derivatives, I want to look at 0.7. Oh, sorry, negative 0.7, 0.7, and the values in between. So to the left of negative 0.7, between negative 0.7 and 0.7, to the right of 0.7. So my second derivative is 0 here and here. And let's just see it. It's 12x squared minus 6. So if I have a value less than negative 0.7, negative 1, for instance, 12 times negative 1 squared is still positive 12. Take away 6 is still positive. Between negative 0.7 and positive 0.7, 0 would be a great choice. That's negative. And greater than 0.7, this is a jagged smartboard. 1 would be a great choice, and you would get positive. So this tells us about our concavity. It is concave up. It is concave down. It is concave up again. So we have points of inflection. These are really important points. We want to make sure we cover those when we're choosing some points. So step number 7 is to make sure that we have some really good and helpful points. We have some great intercepts, but we should have our critical points, and we should have our points of inflection. Okay. To make sure that I get those on there, in fact, I'm just going to critical points. So I just used a calculator with my original function. Check my math, please. Negative 2.6 and 0.2. So I'm going to put these on my graph. I like to label them so that I remember where I have points of inflection and critical points. And I know where my concavity changes, and so I can make myself a smooth curve. Okay. So some points that I have, my intercepts are 0, 0. 1, 0 is a double real root. So I'm going to make a note of him. And negative 2. I have a critical point at negative 1.4, negative 4.8. And another critical point at 0.4, 0.3. So silly on a smartboard. And at 1, 0, and I already have that as an intercept. I have 2 points of inflection. One is at negative 0.7, and it is negative 2.6. Sorry, just a little bit over there. And I have 0.7 and 0.2. Okay, this is ridiculous. I should have changed my scale. I'm just going to finish this and maybe change my scale in a second. I have a point of inflection where the blue thing is. I've got to change concavity there. So it's going to change from concave down to concave up. It is concave down until the other blue point. And then it changes to concave up. And lumps in the smartboard. It is crazy, crazy bad. Okay, with that abysmal graph on the lumpy smartboard, I just quick put it into Desmos and cheated so you can see where it changes shape. We've got a change of concavity at about negative 0.7. So in about here, and it would be concave down until right there. And we can see that change in concavity. And we can see that max and the min value at our critical points.